Today I'll be presenting the solution to the first practice problem in homework number 4. Okay, so let's restate the problem. We're going to do that with our picture as we've been doing. So we have buried under the ground a sphere of nuclear waste that is decaying. It is buried 10 meters underground. We will call that Z. And we know that the sphere is 2 meters in diameter. That's quite a bit of nuclear waste. We also know two temperatures. We have T1, the temperature on the outside of the sphere, and we have T2, which is the temperature of the surface. Okay, so we know that this is buried in soil that will have a thermal conductivity K. Alright, so everything being stated, we need to know the thermal conductivity, which isn't given in the problem statement, but remember, you can look those up in the back of the book. So looking up the thermal conductivity for soil, as this is buried underground, in table A3, we find it is 0.52 watts per meter Kelvin. Okay, so our approach for this problem, since we're going to have heat flowing in multiple directions, not just 1D, then we need to not make a 1D assumption, but instead to use two-dimensional approaches for heat conduction. In this case, we're going to use a conduction shape factor. Remembering that a shape factor is just a tabulated solution to the heat diffusion equation for specific scenarios. In this case, we go to table 4.1 in our book, and that's going to show us a lot of different scenarios we have. We find one that matches, we apply it. So, let's go ahead and do it. Our analysis. We're going to start by stating our assumptions, which are steady state heat conduction, so nothing's changing with time. And also, since we're modeling the the heat conduction through the soil, we actually don't have any energy generation in the soil, so we're going to say no gen. Okay, we go to table 4.1 and we look at our cases and we see case number 1 looks just like this. So we look up the conduction shape factor in table 4.1 for case 1, and that is 2 pi d over 1 minus d over 4z. Okay, and that stipulates that z must be greater than d divided by 2, which, just looking at our numbers, we are definitely satisfying that restriction. That is a restriction, which is also in the table. Okay, we have our shape factor. The question is, how do we use our shape factor? Well, we're going to use this equation given right above the table, which is S, our shape factor, times K, times the difference in temperature. Okay, now it just remains to plug in our values. So we will just plug in this S into this equation, which gives us 2 pi d over 1 minus d over 4z. This marker is dying, so I'm going to switch. Thank you. Okay, so just writing that out a bit more clearly, plugging our shape factor S into our heat transfer equation. That's a Z. So we plugged in S, we know K, and we know delta T. All right, so we know D, we know Z, we know T2. I didn't actually finish specifying our problem. We were asked to find T1, where we know that the Q from our radioactive waste is equal to 500 watts. So we know Q, we know all variables except for the surface temperature of our radioactive waste. So solving for T1, the thing we want to know, we get this. Okay, all we have to do is plug in values, and we end up with a T1 of 92.7 degrees Celsius. Now, I've been neglecting to add discussion, so I'm going to do that now. And my point of discussion here is, I don't like this problem. The reason is, you'll remember we talked about in class that a conduction shape factor, this equation, gives you the heat rate between surfaces 1 and 2. Now in this problem, the only thing they told us was the total heat generated by the nuclear waste, which we can't guarantee all of that is going to the surface, as we don't know what's happening with the soil. So I'm not sure if I believe this answer myself, but this is nonetheless how you would use a conduction shape factor. Okay, our last very brief point is we are asked to draw isotherms, which are constant temperature lines. So we know the temperature of the top surface is constant, so isotherm will look like this. Now these isotherms will begin to curl around like this, going downwards into the colder dirt below. And then we know that this is at an elevated temperature, and we're asked to draw heat rate lines, which, remember, the most important point is those heat rate lines are always perpendicular to our isotherms, or lines of constant temperature. So we know heat's going to go straight towards the surface, but it's also going to follow these 2D routes going off to the side and approaching the surface. Okay, that is the solution to our first practice problem in homework 4.